Hello, my name is Ethan, and today we'll be learning about area ratios. So, if we have a triangle with a base of 6 and a height of 4, how would you find the area? Well, you would probably use area is equal to 1/2 base times height. Plugging the values in, we have 1/2 of 6 times 4, or 12. Okay, now what if we have the same triangle? But now we take a vertex and split it to the other side, splitting this base of 6 into two bases of length 3 and 3. And the congruent sign is these tick marks here telling us that the lengths are equal. So let's try to find the areas of the yellow triangle and the green triangle. And we're given that the height is 4. Well, remember, when we're finding the area of a triangle with 1/2 base times height, the height is the perpendicular distance. For example, for the yellow triangle, it would be this value here. We take the vertex and draw a right angle. So this actually means that the height for the yellow and green triangles are the same. They're both 4. And this is like the crucial idea behind area ratios. So if we calculate it out, the area of yellow is 3 times 4 divided by 2, the area of 6, and the area of the green is also 3 times 4 divided by 2. So it is really interesting why the two areas are the same. And this is because these two triangles share the same altitude of 4 and also have the same base of 3. Because area is 1/2 base times height, those are the only values that can affect the area. Now, this idea goes the other way as well. If we're given that the areas of the two triangles are 6 and 6, we're actually able to determine that the ratio of the side lengths here, well, we can determine the ratios 1 to 1 or that they're congruent. And this is also because of the fact that their heights are the same. Now let's take an example. Take a look at if the ratio is different. Let's say if it's 5 to 1. If the base of the yellow triangle is 5 and the base of the green triangle is 4, and the height is also 4. The area of the yellow triangle would be 5 times 4 divided by 2, or 10, and the area of the green triangle would be 1 times 4 divided by 2, 2. Now stop and think. Is there anything interesting with the numbers in this problem? Well, if you notice something between 10 and 2 and 5 and 1, you'd be right. The ratio of the areas between the yellow and green triangles is 10 units squared by 2 units squared. And the ratio of their base lengths are 5 to 1. And these ratios are actually the same. And this is what we expected because when we find the area, we're just multiplying the base and the height. So the bases are like directly proportional to the area when the height stays constant, which it does at 4. In general, this works both ways. So in this problem, we went from the ratios of 5 to 1, the side length ratios, to the area ratios, which is 10 to 2. This goes the other way because it's a ratio, and let's just see in the general case, how could it work? So we don't even need the height for this. If we know that the area of the yellow triangle is x, the other one's y, and has a base of a and a base of b, for some height, we don't need to know what it is, just that the fact that the yellow and green triangles both have the same height, the same value height, then we can find out that the area of the yellow triangle, which we'll write over here, is 1/2 times A times H. The area of the green triangle is 1/2 times B times H. So you see, they're very similar. They both have the 1/2 in H terms. They only differ by the side length ratios of A and B. That's why what we have is this relationship. If two triangles share an altitude, then the ratio of their areas, in this case, the ratio of the yellow triangle area to the green triangle area is x over y, is equal to the ratio of their bases. In this case, the yellow base is length A and the green base is length B. So overall, this is a very powerful tool. So anytime you see ratios of side lengths, you know that you can find the areas. Anytime you can find the ratio of the areas, you can find the ratio of the side lengths. And if you know one of the values, then you can solve the entire triangle. Used in this case, where we have one big triangle split down the middle into two. However, it's important to know that this only works when they share the same height. So if you have something like, say, this, okay, say you wanted to compare this green triangle here with this yellow triangle, you actually would not be able to use these bases and say that the areas have a proportion with the bases because their heights are not the same. One is obviously taller than the other. And also, one last thing, even though this is typically used when the two triangles are together, specifically when their bases form a straight line, it could also work when they're separate and just that their altitudes have the same length. Okay, now we learned about area ratios, let's see the power of it in full action with the 2006 AMC 10B problem 23. So, a triangle is partitioned into three triangles and a quadrilateral by drawing two lines from vertices to their opposite sides. The areas of the three triangles are 3, 7, and 7 as shown. What is the area of the shaded quadrilateral? So I encourage you to take a moment and think how we can solve this problem with area ratios. But the first thing that jumps out to me is the areas of 7 and 7. Remember what this means. Because the areas are the same and they share the same height, we know that their bases are the same. We can denote this in congruence tick marks right over here. And to reiterate, this is because if we were to draw out the altitude, it'd be the same length, whatever it is. Okay, so that was pretty fruitful. We looked at the ratio of areas and we were able to come out with a ratio of sides. In this case, 1 to 1. Let's try this with the areas of 3 and 7. Because the triangles, this triangle and that triangle, have ratios in 3 to 7, we can say something about their bases, with this length being something like 3x and the other length being something like 7x. Okay, but how does this help us find the area of our quadrilateral? Remember, our area ratios method mainly works for triangles. So why not split the quadrilateral into two triangles? They're easier shapes to work with, and we might be able to use some of our area ratios. So the first thing I like to do is use the red area ratio again, because 1 to 1 is honestly pretty easy to work with. But before we work with the two triangles of the quadrilateral, we should first call them something like A and B for their areas. So if we look at the red area ratio of 1 to 1, so let's just call it the red ratio. If we draw out the triangles here, so we have a yellow one and a green one. Okay? Because the ratio of the lengths is 1 to 1, we know that the area of the yellow triangle, which is 3 plus b, over the area of the green triangle, which is just a, is equal to 1 over 1. Cross multiplying, we have a is equal to 3 plus b. So this gives us one part of the quadrilateral in terms of the other, which is very helpful because if we get another equation, then we can find the values of a and b and then find them and then sum them to find the area of the quadrilateral, because our end goal is finding a plus b. Next, let's use the 3x to 7x ratio we found. Let's just call it the blue ratio. So now we're looking at a different set of triangles. Try to see if you can find the triangles yourself, but it's this pair in yellow and green. So the area of the yellow triangle is just B. The area of the green triangle is the A triangle plus the 7 triangle. And this is equal to their ratio of their bases, which is 3x to 7x or 3 to 7. Cross multiplying, we have 7b is equal to 3a plus 21. And now we have two variables and two equations. So we just need to substitute the first one into the second one and we can solve. So let's just do that real quick. We have 7b is equal to 3 parentheses 3 plus b plus 21. 7b is equal to 3b plus 9 plus 21. So move the 3b over, collect the terms. 4b is equal to 30. B is equal to 30 over 4, or 15 over 2. Now, to find a, we just need to plug it back in to a is equal to 3 plus b, which tells us that a is equal to 3 plus 15 over 2. We could add these two fractions together, but even better, realize that we're looking for a plus b, so if we just add another 15 over 2, the two 15 over 2's just become 15, and a plus b is 3 plus 15, which is 18, our final answer. So the area of the shaded quadrilateral is 18. Thank you so much for watching, and if you'd like further practice with area ratios, we're going to put up a collection of problems on the screen right now. Bye.